Good morning, everyone. My name is Khushi from BSc Chemistry Honors, second year, and today my chapter is Nitro Compounds. Introduction. Nitro compounds are an important class of organic compounds which may be regarded as derived from hydrocarbons by the replacement of one or more hydrogen atoms by nitro NO2 groups or and nitroarenes group is directly attached to benzene ring can be prepared rather easily or have been used as synthetic reagents since long. Structure of nitro group. Nitro group is quite often represented as containing a double bond between nitrogen and one oxygen and a coordinate or dative bond between nitrogen and other oxygen and double bond O and a coordinate bond between nitrogen and oxygen. But actually nitro group is stabilized established by resonance and is a hybrid of two equivalent contributing structures. The resonance hybrid structure is confirmed by the fact that the bond length of each nitrogen oxygen is 1 to 1 picometer or 1 to 1 angstrom. Nomenclature of nitro compounds. Nitro compounds are named by writing the word nitro before the name of parent compound. For example, nitromethane, nitroethane, 2-nitropropane, 2-nitro-3-methyl-butane. Classification of nitroalkanes. Nitroalkanes are termed as primary, secondary, or tertiary according as the nitro group is attached to a primary, secondary, or tertiary carbon atom. That is primary nitroalkane, secondary nitroalkane, tertiary nitroalkane, nitroethane, which is primary, 2-nitropropane, which is secondary, 2-methyl 2-nitropropane, which is tertiary. Preparation of nitro compounds. Preparation of nitroalkanes. Nitroalkanes are usually prepared by following methods. Vapor phase nitration of alkanes. This reaction involves the substitution of a hydrogen atom of the alkane by a nitro group. It is carried out in a vapor state by heating the alkane with nitric acid at about 700 Kelvin. Limitation of the process. During nitration of higher alkanes, all the possible isomeric nitro products are formed. Due to the formation of complex mixture of products, this method is used for the laboratory preparation of nitroalkanes. However, this method is widely used for commercial preparation of nitroalkanes. Mechanism. The reaction is believed to involve the formation of free radicals, but the mechanism is not well established. Second, action of silver nitrite on alkyl halides. This method is generally employed for the laboratory preparations of nitroalkanes. When heated with silver nitrite, the alkyl halide undergo nucleophilic substitution to form nitroalkanes along with small quantities of alkyl nitrites. However, the mixture of alkyl nitrites and nitroalkanes can be separated by fractional distillation. Third, oxidation of amines. When an amine amine in the in which the amino group is attached to a tertiary carbon atom is oxidized with potassium permanganate, a tertiary nitroalkane is absorbed. Preparation of nitroarenes. Nitroarenes are almost invariably prepared by the direct nitration of arenes. The nitrating agents generally used are concentrated or fuming nitric acid, mixture of concentrated or fuming nitric acid and concentrated sulfuric acid, sometimes fuming sulfuric acid is also used. This mixture is most commonly used as nitrating agent. Third, mixture of concentrated nitric acid and acetic anhydride or boron trifluoride. Fourth, acetyl nitrate, which is CH3COONO2, obtained by mixing nitrogen pentoxide and acetic anhydride. Fifth, nitrogen peroxide in the presence of anhydrous aluminum chloride. Choice of nitrating agent. The choice of nitrating agent is to nitrating agent to be used for nitration for a given compound depends upon the following factors. First, nature of compounds to be nitrated, number of nitro groups to be introduced. In the nitration of aromatic compounds containing electron releasing or activating group such as NH2, OH, CH3, the reaction takes place radially at room temperature by employing concentrated HNO3. In some cases, even dilute HNO3 can be used. Mechanism of nitration. Nitration of aromatic compounds like other aromatic substitution reaction is electrophilic in nature and involves a nitronium ion which is NO2 positive as the attacking electrophile. The mechanism may be summed up as follows by considering the nitration of benzene ring with nitric acid sulfuric acid mixture. Generation of electrophile HONO2 plus 2HSO4 will give nitronium ion. Evidence in the favor of above mechanism. It has been shown above the aromatic nitration involves a stepwise mechanism. The nitronium ion, which acts as an electrophilic reagent, is generalized in a preliminary step and being about further reaction in two steps. The first step is a slow rate determining involving the addition of nitronium ion to the aromatic ring to form a carbocation intermediate. The second step, which relatively fast, involves the elimination of a proton from the intermediate ion by the heterolytic cleavage of CH bond. The mechanism has been fully supported by isotope tracer technique as explained. If an aromatic compound labeled with deuterium is subjected to nitration, it is found that the rate of substitution of deuterium is the same as that of ordinary hydrogen or protium. In other words, no isotope effect is observed. Chemical reactions of nitroalkane. Acidic nature. Tautomerism. Nitroalkanes containing alpha hydrogen, primary and secondary nitroalkanes only, exhibit acidic behavior and form salt in the presence of strong alkalines. The acidity can be attributed to the fact that nitro group has a strong electron withdrawing inductive effect. Second, the anion formed after the removal of the proton from nitroalkane gets resonance stabilized due to the ability of nitro group to accommodate negative charge as shown. It is interesting to note that if the salt formed by nitroalkane is acidified at low temperature, the oily drops of nitroalkane do not separate immediately, but we get another form of nitroalkane known as acetylnitro form, which slowly changes into nitroform. The tautomeric equilibrium between the two forms lie almost completely towards the nitro form because it is stabilized by the resonance of nitro group. Acetylnitro form is relatively stronger than nitro form. Reduction of nitroalkanes. The reduction of nitro groups is one of their most important reaction. Reduction in the acidic medium. When reduced in acidic medium, nitroalkanes from primary amine. Catalytic reduction or reduction with lithium aluminum hydride. Reduction with lithium aluminum hydride or H2 in the presence of nickel, palladium or platinum catalyst also yields the same product. Reduction in neutral medium. If the reduction is carried out in a neutral solution, a hydroxylamine derivative is obtained. Hydrolysis. When boiled with concentrated HCl or H2SO4, primary nitroalkanes undergo hydrolysis to form carboxylic acid and the corresponding salt of hydroxylamines. Secondary nitroalkanes are also hydrolyzed to ketones in nitrous acid by boiling with concentrated HCl. Tertiary nitroalkanes or nitroarenes are not hydrolyzed by acids NEF reaction. When sodium salt of primary secondary nitroalkanes are hydrolyzed by boiling with dilute sulfuric acid aldehydes ketones. The reaction proceeds through the acetylnitro form of nitroalkanes. In this reaction, the acetylnitro form act as an electrophile. Action with nitrous acid. Primary, secondary, tertiary exhibit different behavior towards nitrous acid. Primary nitroalkanes react with nitrous acid to form nitrolic acids which dissolve in NaOH to produce a red solution. Secondary nitroalkanes react with nitrous acid to form pseudonitrols which have blue color but do not dissolve in NaOH. Tertiary nitroalkanes or nitroarenes do not react with nitrous acid since they do not contain any alpha hydrogen atom. The above reaction. Sixth, halogenation. When treated with halogens such as chlorine or bromine in slightly alkaline solution, primary and secondary nitroalkanes undergo halogenation at alpha position. Second, catalytic reduction. Reduction of nitrobenzene with H2 in the presence of nickel or platinum catalyst also lead to the formation of aniline. Reduction in neutral medium. When reduced in a neutral medium with zinc dust and ammonium chloride solution, the reaction stops at hydroxylamine stage. Fourth, reduction in alkaline medium. On reduction in alkaline medium, nitrobenzene yields different products depending upon the nature of reducing agents employed. There is sufficient evidence to show that azobenzene is formed through the intermediate formation of exobenzene is further reduction. Reduction with LiAlH4, reduction with lithium aluminum hydride. Reduction of nitrobenzene with lithium aluminum hydride also yields azobenzene. Electrolytic reduction. When reduced electrolytically in a weakly acidic medium, nitrobenzene gives aniline, but on electrolytic reduction in strongly acidic medium, nitrobenzene yields p-aminophenol due to rearrangement of p-hydroxylamines first formed. Seventh, selective reduction. In case of compounds containing more than one nitro group, it is possible to carry out selective reduction to one of the following employing a mild reagent such as ammonium hydrosulfide, which is NH4SH, or sodium polysulfide, which is Na2SX. Electrophilic substitution. Nitro group, being an electron withdrawing group, has a strongly deactivating effect on the electrophilic substitution reaction of benzene nucleus. However, under strong conditions, nitro compounds may undergo electrophilic substitution in meta position with respect to the nitro group. Fourth, nucleophilic substitution. The nitro group has no doubt a deactivating influence on electrophilic substitution in benzene nucleus due to its electron withdrawing nature, but is very electron withdrawing influence of nitro group makes the benzene nucleus liable to attacked by nucleophilic reagents. Thus, unlike benzene, nitrobenzene on heating with sodium hydroxide gives small amounts of ortho and para nitrophenols. Mechanism is given below. Replacement by nitro group. In case of polynitro compounds, one of the nitro group itself can be replaced by nucleophilic groups. For example, benzene ring NO2 NO2, p-dinitrobenzene. In the presence of 2NH3 will give p-nitroaniline, which is benzene ring NH2NO2 plus N2 plus 2H2O, and p-dinitrobenzene in the presence of KOH will give p-nitrophenol plus KNO2, and in the presence of C2H5ONA it will give p-nitrophenol tol plus NaNO2. That's all about our chapter. Thank you for listening. Nitro compounds.